Hey guys, welcome back to another lecture video for Chem 115. In the previous lecture video, we learned how to determine the complete rate law from a given set of kinetic data that contains only two reactants. In this lecture video, we will learn how to determine the complete rate law for a chemical reaction that has three reactants. Also, we will learn how to determine the rate law from a given set of kinetic data in which the initial concentration of reactants among experiment 1, experiment 2, experiment 3, and so forth do not cancel. So we're going to go ahead and look at that scenario near the end of this lecture video. So let's go ahead and get started with our first example. Here we see three reactants: bromate ion reacting with 5 moles of bromide ion and 6 moles of hydrogen ion. Now, the products for this chemical reaction is going to be 3 moles of diatomic bromine and 3 moles of H2O, or water. And so the main point of this example is to determine the rate law based on the kinetic data that was collected from this chemical reaction at 30 degrees Celsius. And so if this experiment was ran at 25 degrees Celsius, the rate constant K would be different, and so therefore the experiment itself has to be redone at 25 degrees Celsius, and a new kinetic data needs to be collected. Anyways, that's besides the point. And so once again, the main goal of this example is to determine the rate law. And so what we're going to do is we're going to write the general rate law for this chemical reaction that's being ran at 30 degrees Celsius. And so the rate of the reaction is equal to, and we're going to go ahead and skip this part for now, so just ignore this. It's going to equal to the rate constant K times this by the concentration of bromate raised to the m power, the concentration of bromide ion raised to the n power, and the concentration of hydrogen ion that's raised to the p power. And so this exponent doesn't have to be p, it can be o, it can be a, it can be b, it doesn't really matter, it's just a variable. And so to help us organize our work, since we're working with 3 reactants instead of 2, I'm just going to go ahead and write lowercase m above the bromate, lowercase n above bromide, and lowercase p above hydrogen ion. And so once again, the main goal of this example is to figure out the orders of reaction, the value for the orders of reaction, as well as the rate constant K. And once we have all 4 of these pieces, then we can go ahead and write the complete rate law for this reaction that's being ran at 30 degrees Celsius. So if you recall from the previous lecture video, to help us whittle down the number of variables that we're going to be working with, what we want to do is we want to take a ratio between 2 experiments that allows us to cancel, in this case, 2 exponents, leaving us with just 1 variable to work with. And so, for example, if we take a look at the initial concentrations of experiment 1 and experiment 2, we can see that the initial concentration of bromate is different. However, the initial concentration of bromide and the initial concentration of hydrogen ion between experiment 1 and 2 are the same. And so if we were to take the ratio of the kinetic data between experiment 1 and experiment 2, we know that these values are going to cancel out, enabling us to cancel n and p. And that will leave us with just 1 variable, which in this case is lowercase m, and we can go ahead and figure out the orders of reaction based on what's left over. And so we'll go ahead and do just that. So what I'm going to do is I'm going to write a ratio of the rate law between experiment 1 and experiment 2. And so the rate of the reaction for experiment 1 is 8.0 times 10 to the negative 4 molarity per second. And the initial rate for experiment 2 is going to be 1.6 times 10 to the negative 3 molarity per second. And so if this is the initial rate of the reaction, then the initial rate of the reaction can be expanded to the general form of the rate law. So the rate constant K times this by the concentration of bromate raised to the m power times this by the concentration of bromide raised to the n power times this by the concentration of H plus raised to the p power. And so I'm going to go ahead and duplicate what I wrote just to save time. And I'm going to put that in the denominator because I would have to expand what the initial rate is for experiment 2. Okay. And so since we're comparing experiment 1 and experiment 2, the only thing that's left for us to do is to just basically fill in the concentrations that's found in experiment 1 and experiment 2. So we're just going to go ahead and plug this guy into here. We're going to plug this guy into here. And then this 0.10 and 0.10, they're all going to be plugged into their respective places. Okay. And so I'm just going to go ahead and rewrite that very quickly. So let me duplicate this. And so this bromate, it's going to be 0.10 at the top, 0.20 at the bottom. The bromide, okay, according to our kinetic data, the initial concentration is 0.10, 0.10. And for hydrogen ion, H+, it's also going to be 0.10, 0.10. And so if you look at what we filled in, we can cancel the values for K, because the rate constant is the same if the reaction is performed at the same temperature. We can also cancel these two parts out, leaving us with just the ratio of the initial rate and the ratio of the initial concentration with respect to the order of reaction M. Okay. And so I'm going to go ahead and type this, plug this into my calculator. So 8.0 times 10 to the negative 4 over 1.6 times 10 to the negative 3. And so if I'm not mistaken, that's going to be 0.50. And in this case, the units do cancel. And that's going to equal to, once again, just this section over here. And I'm going to get 0.10 over 0.20. I'm going to factor out that m. And if I were to reduce what's inside the parentheses, that's also going to be 0.50. Now, you guys can go ahead and tackle or solve for the value of m in one of two ways. You can think about this logically. What value of m, what value of the exponent, will allow 0.50 to equal 0.50. Now, if you guys don't know that, you guys can go ahead and use properties of log to figure that out. And so the quick answer to this is 1. If the exponent is 1, then 0.50 is equal to 0.50. But if we were to take the route in which we're going to use properties of log, then we're going to go ahead and write log of 0.50 is equal to log of 0.50 raised to the m power. And that's going to allow us to use the properties of log to move that exponent in front of it. And so we would have m times this by the log of 0.50. And then we're going to go ahead and I'm just going to carry this at the bottom. Let me duplicate it. Let's see here. I'll just go ahead and rewrite it. So here I have log of 0.50, log of 0.50. And so if I divide log of 0.50 on both sides, and I plug that into my calculator, the value of m that I'll get is equal to 1. And so I can go ahead and update my rate law. I'm just going to go ahead and copy this section okay, such that the rate of the reaction at 30 degrees Celsius is equal to the rate constant K times that by the concentration of bromate raised to the first power. Okay. And so notice that since I solve for m, that means the value of m is going to go towards bromate, not bromide, not H+. So you want to make sure that you're placing those orders of reaction correctly in the general rate law equation. So now that I've solved for bromate, I'm going to go ahead and repeat this to figure out the value for N and to figure out the value for P. And so for us to do so, we're going to look at our given kinetic data. And we're going to look for two more experiments that allows us to cancel two of these reactants, leaving just one alone. And so if you look at experiment 2 and experiment 3, notice that the bromate is the same. So we know that if we plug this into this equation, the concentration of bromate will cancel, and the concentration of hydrogen ion will also cancel if we plug it in to this equation. And if you look at bromide, the concentration is different, and so therefore the value for N can be solved. Okay. And so for this second round, I'm just going to go ahead and skip some steps. So since I know that bromate is going to cancel and H+ is going to cancel, I'm just going to go ahead and write the ratio between bromide and the initial rate of reaction. Okay. And so the initial rate of experiment 2 over the initial rate of experiment 3 is equal to some number, and that's going to equal to the concentration of bromide from experiment 2 raised to the n power times, or divide that by the concentration of bromide from experiment 3 raised to the n power. And so all we have to do now is just plug in the initial rates and plug in the concentration. So the rate for 2 is going to be 1.6 and 3.2 times 10 to the negative 3 for experiment 3. Okay. And so the concentration for bromide for experiment 2, I believe, is 0.10 molar. Right? So here I have 0.10 molar and 0.20 molar. Okay. And so if I were to plug this into my calculator, I'm going to get 0.50. And once again, the units will cancel. And if I plug this into my calculator, this is going to be 0.50 as well. And so once again, you guys can either ask yourself what exponent will allow 0.50 to equal to 0.50, or you guys can more accurately figure it out by using properties of log, much like what we did in this previous section. And so it turns out that the value for n is equal to 1. And so what we're going to do is we're going to update once again our rate law. So now that we solved for the value of n, we're going to go ahead and erase n and replace that with a value of 1. So the last thing that we need to solve for is the order of reaction p. So very similar to what we've done in the prior two examples. We're going to look at two experiments that will allow us to cancel bromates and bromides, since we already figured that out, leaving us with just a concentration of hydrogen ion and P to solve for. And so looking at this table, I want you guys to focus on experiment 1 and experiment 4. Notice that 0.10 cancels with 0.10, and 0.10 for bromide cancels with a 0.10 for bromide in experiment 4. And so if you look at the initial concentration for hydrogen ion, they are different, and so therefore the P will not be canceled. Only M and N will cancel, since the concentrations are the same. So once again, we're going to take a ratio between experiment 1 and experiment 4. Okay. And so since I know that the concentration of bromate and bromide is going to be canceled, I'm not going to go ahead and include that in my calculation. It's just going to save us some time in terms of doing the problem. And we know that the rate constant K is going to be canceled out between both of these experiments. And so what we're doing is we're just trying to figure out the concentration of H plus. So this is H plus over here for experiment 1, and that's going to be 0.10. And for experiment number 4, it's 0.20, if I recall correctly. Yep, so 0.10 and 0.20. Now the initial rate is going to be 8.0 times 10 to the negative 4 and 3.2 times 10 to the negative 3. Okay. So it's going to be 8.0 times 10 to the negative 4 molarity per second, and 3.2, I believe, 3.2 times 10 to the negative 3 molarity per second. Let me just double check that. Yeah, 3.2 and 8.0 times 10 to the negative 3, negative 4. All right, so let's go ahead and plug this into the calculator real quick. So here we have 8.0 times 10 to the negative 4. Divide this by 3.2 times 10 to the negative 3, and that's going to give us 0.25. And so 0.10 divided by 0.20, that's going to give us 0.50 raised to the P power. And so once again, you guys can go ahead and ask yourself what value of this exponent P will allow 0.50 to equal to 0.25. And if you guys don't know that on top of your head, that's okay. You guys can go ahead and use rules of logs to help you solve the value for P. And so I'm going to go ahead and take the log of 0.25 and make that equal to the log of 0.50 raised to the P power. So taking the log of both sides allows us to move this P to the very front. And so this is going to equal to log of 0.25 equals to P times this by the log of 0.50. And so I'm going to go ahead and solve for P. by dividing both sides by log of 0.50. Now, if you guys plug this into your calculator, the value of p that you guys should get is 2. Okay, and so I encourage you guys to use your parentheses to just kind of make sure that your calculator is calculating each piece correctly. So it's going to be parentheses log of 0.25 close parentheses, divide that by open parentheses log of 0.50 close parentheses. And so if you plug that in correctly into your calculator, you guys should get a value of 2. And so now I'm going to go ahead and update my rate law once again, my general rate law once again for this chemical reaction. And now that I've solved for the value of p, I'm going to erase the variable p and replace that with the value of 2, the exponent 2. And so we're almost done solving for the complete rate law for this chemical reaction. The only thing that we need to do is to solve for the rate constant k. Okay? And so you guys can only solve for the rate constant k once you have figured out all of the orders of reaction. And so to solve for k, the rate constant, all you need to do is just choose the initial concentration and the initial rate of only one of these experiments. And so you guys can choose any of these experiments, and the value for the rate constant k should be the same or roughly the same. And so looking through this experiment, I guess it's just really easy for me to use experiment 1 just because the initial concentrations are all the same. So it's 0.1 times 0.1 for bromate, 0.1 for bromide, 0.1 for H+. And the initial rate is going to be 8.0 times 10 to the negative 4 molarity per second. Okay. And so the initial rate of 8.0 is going to replace the initial rate of the reaction. So the initial rate of the reaction is going to be 8.0 times 10 to the negative 4 molarity per second. And that's going to equal to the rate constant k times this by, and I'm going to replace the concentration, I'm going to replace this variable of bromate to its actual concentration for experiment 1. So I'm using the data from experiment number 1. And so this is going to be 0.10 molar raised to the first power times this by 0.10 molar raised to the first power times this by 0.10 molar raised to the second power. Okay. And so I'm going to go ahead and plug this into my calculator. So I have 0.1 squared times this by 0.1 times that by 0.1. And so what I'm going to get is 1.0 times 10 to the negative 4. Now let's go ahead and talk about units. So when you multiply all three of these, you have to consider what the overall unit is after multiplying all three of those terms. And so you can go ahead and distribute this exponent to the unit. And so what we get is going to be molarity to the first times this by molarity to the first times this by molarity to the second. And whenever you multiply with different exponents, or with exponents just in general, what you're really doing is you're adding the exponents. So this is going to be m to the fourth power. Okay. And so if we have 8.0 times 10 to the negative 4, molarity per second, that equals to the rate constant K times this by 1.0 times 10 to the negative 4 molarity to the fourth power. We're going to go ahead and solve for K by dividing this 1.0 times 10 to the negative 4 to the other side. So I'm going to go ahead and divide this to the other side. And the value for K, or the rate constant K, is going to be, let's see here, so it's going to be 8.0 times 10 to the negative 4 divided by the answer. And that's going to be 8.0. Now, the last thing that you want to focus on is the units. Here in this case, the units is going to be 1 over molarity to the third times this by second. And so how did I get that? Well, I can always use the rules of division for fractions. So here, if I have molarity per second, divide this by m to the fourth. This is the same as saying m to the fourth over 1. And so I'm going to go ahead and keep, change, and flip. And so what I get is molarity per second, change the division to a multiplication, and then you flip this fraction. So it's going to be 1 over m to the fourth. So if you cross multiply, that is going to equal to 3. And when you multiply across, you just get 1 over molarity to the third times this by second. All right, and so now that we've figured out the value and the units for the rate constant K for this chemical reaction, we're going to go ahead and write our final rate law, such that we have the rate of the reaction is equal to 8.0, 1 over molarity to the third times second, times this by the concentration of bromate raised to the first power. It's following first order kinetics, times this by the concentration of bromide raised to the first power. Once again, it's following first order kinetics, and the concentration of hydrogen ion raised to the second power. So the hydrogen ion is following second order kinetics. However, the overall order of reaction is fourth order, right? It's just the sum of all of the individual orders of reaction. So this whole chemical reaction is undergoing, or not so much undergoing, but it's following fourth order kinetics. And so this would be the complete general rate law for this reaction that's being ran at 30.0 degrees Celsius. Okay, and once again, if this reaction was ran at a different temperature, you would have to go back and rerun all 4 of those experiments, collect new kinetic data, and then perform these calculations to determine the order of reaction, as well as the rate constant K. And so once you guys have the rate law for this chemical reaction, as long as this reaction is at 30 degrees Celsius, then you can go ahead and plug in any concentration value for these reactants to observe or quantify how the rate of reaction is going to change. And so, for example, if we double or triple the concentration of bromate, if we have the concentration of bromide, and if we quadruple the concentration of hydrogen ion, how is the rate of reaction going to change when it's compared to the concentration that is 0.10, 0.10, and 0.10, or something like that. So that's really the power behind these rate laws. We have the ability to predict the rate of the reaction once we know the rate constant K, as well as the orders of reaction. All right, and so for the second example, we're going to go ahead and take a look at how to solve the complete rate law based on concentrations between two or more experiments that is not the same. So reading this problem, let's see here. So it was determined that the order of reaction for reactant A, which is this, is second order. So already this problem is telling us the value for M for reactant A. And we want to determine the overall rate law based on the experimental data that's collected. So here in this case, we're only focusing on two experiments, experiment 2 and experiment 3. And so this reaction has nothing to do with a previous example. This is just a whole new example, whole new scenario. And so I want you guys to look at the initial concentrations. And so notice that the initial concentrations of A is not the same, and the initial concentration of B is not the same for these two experiments. And so what do we need to do to solve for the rate law if we're not able to cancel out any of these concentrations when we take the ratio of two experiments? Okay. Well, fortunately, we were able to determine, or it was already given to us, that the order of reaction for M, which reflects reactant A, is undergoing or following second order kinetics. And as long as we have at least one of the pieces determined, we can solve for the order of the reaction for another reactant, in this case B. And so to set this up, we're going to treat this like a general method of initial rates problem, in which we're going to take the ratio between experiment 2 and experiment 3. So here we have the rate of reaction for experiment 2 over the rate of reaction for experiment 3 is equal to, so here we have 5.0 times 10 to the negative 7 molarity per second divide this by 4.0 times 10 to the negative 6. And so this is what the initial rates are for these two experiments. And then that's going to equal to the rate constant K times this by the concentration of A raised to the second power. Remember that we know, based on the problem, we know that reactant A is undergoing or following second order kinetics. So this is for experiment 2 over the rate constant K times this by the concentration of A raised to the second power times this by the concentration of, in this case, B raised to the n power. So we don't know the value for B. We don't know the value for the order of reaction for B, but we do know the order of reaction for A. And so we're going to assume that this kinetic data, or this experiment, these two experiments, was performed under the same temperature. So therefore, the rate constant k can cancel out. And so if I plug this into the calculator, 5.0 times 10 to the negative 7, divide this by 4.0 times 10 to the negative 6 is going to give me 1.25 times 10 to the negative 1, or just simply 0.125. And so here in this case, the units is going to cancel, so I just have 0.125. Now, since I know the concentrations, the initial concentrations of A and B, I'm just going to go ahead and plug them in based on the kinetic data. So the concentration, the initial concentration for A is going to be 0.063. Raised to the second power over concentration of 0.100 raised to the second power times this by the concentration of 0.063 for B raised to the n power over the concentration of 0.200 raised to the n power. Okay. And so looking at this piece, we can go ahead and plug this into our calculator. So we're going to go ahead and reduce that. So 0.125 is equal to, let me go ahead and type that into my calculator. And what you guys can do, you guys can actually factor out the squared. So let me go ahead and rewrite this. So 0.063 over 0.10 times this by 0.063 over 0.20. Okay. So here we have 0.063, divide this by 0.10, and we're going to go ahead and square that value, and that's going to give us 0.3969 times this Okay, so here I have 0.063. Divide this by 0.200. It's going to give us 0.315. Okay. So in terms of sig figs, I'm just going to keep so this is 2 sig figs, this is 2 sig figs. So I'm probably just going to make a note that I'm going to keep 2 sig figs in my final answer. But for now, I'm just going to keep the raw answers. And so all of this is going to equal to 0.125. And I'm going to go ahead and reduce this by dividing this term on both sides. Okay, so that's going to cancel this out. And I'm going to get, so 0.125, divide this by 0.3969. So that's going to go ahead and give me 0.31. Okay. And that's going to equal to 0.31 and so if I just keep 2 sig figs, that's approximately 0.32. This is raised to the n power. Okay. And so 0.31 and 0.32, they're actually very close to each other. I think the only reason why these values are a little bit off is because of the rounding that I've done in between here. And so we're going to go ahead and treat this. Actually, let's just go ahead and use the properties of log, and you'll see that the answer is going to come out to 1 anyways when you round it. And so let's go ahead and just take the log of both sides. So 0.31 log of, so I'm going to move the n over, so it's n times this by the log of 0.32. So I'm just going to skip a few steps there. And so I'm going to go ahead and divide both sides by log of 0.32. Okay. So if you guys plug that into your calculator, log of 0.31, divide this by log of 0.32. Okay. You guys will get a value that is 1.0278, and the list goes on. And so we're just going to go ahead and keep the correct number of sig figs here. And so the value for that would be 1. Actually, if we're going to do sig figs for log, it's going to be number of places after the decimal. So it's really 1.03. Okay, but we're going to go ahead and round that to the nearest whole number, which is going to be 1. Okay. All right, and so now that we've determined the value for n, which is going to be 1, we're going to go ahead and rewrite our complete general rate law, or I'm sorry, it's still not complete yet because we have not solved for the rate constant k. And so we're just going to go ahead and write the general form of this rate law. So the rate is equal to the rate constant k times this by the concentration of reactant A raised to the second power, because it's following second order kinetics, times this by the concentration of B raised to the first power. So this is following first order kinetics. And so for the rate law to be considered complete, we need to know what the value of k is, as well as its unit. And so to do that, we're going to go ahead and choose one of these experiments. It can be either experiment 1, or it can be either experiment 2 or experiment number 3. So I'm just going to go ahead and use experiment number 2, since the numbers are easy for me to memorize as I go from this lecture slide to the next. So it's 0.063 and 5.00 times 10 to the negative 7. And so the initial rate of the reaction from experiment number 2 is going to be 5.0 times 10 to the negative 7 molarity per second. And that's going to equal to the rate constant k times this by the concentration of A, which is going to be 0.063, molar raised to the second power, times this by the concentration of 0.063, molar, times this by, raised to the first power. Okay. So if I were to reduce this term, I would get 0.063 squared times this by 0.063. Okay. And then here I would get 2.5, 2 sig figs, times 10 to the negative 4. And once again, remember that we have to consider the exponent in our units. So this is going to be m to the third. Right, so it's m, so this is essentially going to be m to the second times this by m to the first. And so when you multiply your terms with exponents, you're basically adding the exponents. So this is going to be 2 plus 1 is equal to 3. All right, and so I'm going to go ahead and solve for k. So I'm going to divide 2.5 times 10 to the negative 4 over to the other side. So here I have 5.0 times 10 to the negative 7. Divide this by 2.5 times 10 to the negative 4. Okay. And so here, if I were to divide this by 2.5 times 10 to the negative 4, I would get 1.99, lots of 9s actually, 62, and the list goes on, times 10 to the negative 3. And so since I have 2 sig figs in since I'm performing division and 2 sig figs is the least, I can go ahead and round this to basically 2.0 times 10 to the negative 3. Now in terms of units, remember that this is molarity per second divided by molarity to the third over 1. So I can keep change flip, so that's going to be molarity over second times 1 over molarity to the third. This is going to cancel out, and this 3 reduces to 2. And so I would get 1 over molarity second times seconds. And so my value for k, including the unit, is going to be 2.0 times 10 to the negative 3, 1 over molarity raised to the second power times this by second. So now that we have the unit for k, we're going to go ahead and write our complete rate law. So the rate of this reaction at whatever temperature this reaction was ran at is going to be equal to 2.0 times 10 to the negative 3, 1 over molarity second times this by the concentration of A raised to the second power, since it's following second order kinetics, times that by the concentration of B raised to the first power. And so this would be our final answer. Okay. All right, so the main point of this specific exercise is to determine the order of reaction when the initial concentrations for each experiment or trial that's given to you is not the same. In other words, if you take the ratio of experiment 2 and experiment 3, these values will not cancel out. And so as long as you know the order of reaction for the other reactants, leaving you with just one order of reaction that's unknown, you can still take the ratio of these two experiments and just plug everything in just like what I did here. So you treat it normally, you plug the initial rates, plug in the concentrations, plug in the order of reaction that was given to you, and then once you guys have everything filled out, just go ahead and solve for that exponent n. All right, so hopefully you guys better understand how to solve for the orders of reaction, as well as the rate constant k, as well as its unit, through these two examples. All right, so I'll go ahead and stop the lecture video here. The next topic that we're going to cover is half-lives and integrated rate laws. See you guys later. Bye.